The second application of uh, the moving charge uniform magnetic field is a mass spectrometer as shown in the figure. In this configuration, this is we call it a brain bridge mass spectrometer. This name comes from its inventor Kenneth Brainbridge that used this configuration to separate the ion of the sample. Okay, if you have a sample and then you vaporize it and then you ionize it, maybe by using the discharge or using the hot filament, or I mean that you give it the energy and ionize it. If you have to, you put the energy large enough to the vaporized material, you can ionize this gas, and then you pass this gas, which can have many isotopes on that. Okay, pass to the velocity selector. Okay, pass to the velocity selector. As we discussed before, that the velocity selector will allow only the particle that have the velocity of E over B to pass to the selector. Okay, you can see that this is the value of V that can pass the velocity selector does not depend on the mass of the particle. So if you have a gas of the isotope, many isotopes, like for example, if you have carbon, for example, okay, may have a carbon 12, carbon 14, and have many isotopes on that gas, and you pass this gas into the velocity selector. If the gas has a velocity equal to E over B, B is a magnetic field in this region, E is the electric field in this region. So any isotope that has this velocity can pass the velocity selector. It's not depend on the mass, because for the same element but with the different isotope, we have the different mass, right? But if they have the velocity of E over B, it can pass the velocity detector. So all isotopes with this velocity can pass this velocity selector. Now, once the particle pass through the velocity selector, we have the slit here again to correct only the particle that move in the straight line. And then the charged particle will enter the second region with the different value of magnetic field. We call this a B0. Okay. Now in this region there is no electric field. So if the particle has a positive charge, like in this figure, we discussed before that the trajectory of the particle will become a circle, right? Because the electric force acts as the central force. So the particle will move in a circular path like this. Okay, and we know that the radius of this circle is equal to mv over q b0. Here b0 is the magnitude of the magnetic field in this region. Okay. Now we have these two relations. This b is the magnitude of the magnetic field in this region. b0 is the magnitude of the magnetic field in this region. Now if we put the value of v here, which is the value of the particle that can pass the velocity selector into this equation, we will have that R is equal to me over q b0b. Okay. This is the radius of the circular path of of the particle that pass through the velocity selector and enter to this region. Okay, you can see that the radius of this circular part is proportional to the value of m, the mass of the particle. If the mass of the particle has the same charge, okay, we will have that the radius is proportional to m. Okay. Anyway, in general, we may not know the charge of the particle. So, if we write the ratio of m over q, it will equal to the r times b0b over e. The value of e, b and b0 can be determined from the configuration of the system, and r is the value that we can measure from the trajectory, or we can measure by put a detector here, and if we know that the particle will move in a circular path, so it will hit the detector somewhere here, and you can measure the distance from the center to the position that the particle hit the detector, and you can measure the radius r. Okay, so we can measure r, b0, b and e can be determined from the configuration of the system. So we can measure the ratio, the mass to charge ratio of the particle. Okay, and as I mentioned earlier, that this system can be used to separate the isotope of an element. Okay, so when the particle with the particle that move past through the velocity selector has isotope with the different mass. Okay, when we ionize the atom or molecule, we ionize the electron that orbit around the nucleus. So the energy that need to ionize the atom or molecule are the same for all isotope, right? Because all isotopes have the same electron and have the same attractive force from the nucleus to the electron, because they all have the same number of proton and neutron. So you have the same attractive potential between proton and neutron. When you ionize the material with a different isotope, for the same amount of energy, you will have the same amount of charge of the ion. Okay, the charge will be the same, but the mass is different. It depends on the isotope that of that particle. Okay, so it means that even though we don't know the value of Q here, we can also calculate the ratio of the mass of the particle that hit the detector by measure the value of R. Okay, the particle that have the large mass will have the large value of R. The particle that has a small mass will have the small value of R. So from that value of R, we can determine the ratio of the mass of the particle, if we know for certain that those particles have the same charge. Okay, so we can measure the ratio of the mass of the particle, and from that ratio, it will related to the mass of the nucleus of that particle. So it means that we can measure how many isotopes that we have in our source. I mean that if we vaporize some element and we want to know how many isotopes in that sample that we vaporize, we put the charge particle, maybe the gas, atomic gas or molecular gas usually it's atomic gas because we want to measure the isotope of the element. Okay, and we put the atomic gas, the gas that already ionized into this velocity selector. Okay, and from the distance r here, we can measure the mass ratio, and then we can determine how many isotopes we have in that sample.